Hi, this is Jason Molesky. In this example, we'll take a look at performing a test for equal proportions. In his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1 is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. Now, to see if the birth date is related to success, which is judged by whether a player makes it to the NHL or not, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. Now, this one-way table summarizes the data on birthdays for these 80 players. We can see that 32 of the players were born between January and March, 20 NHL players between April and June, 16 between July and September, and 12 between October and December. Now, do these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? Well, if they were, we would probably expect to see an equal number of birthdays in each of those 4 quarters. Obviously, we don't see that here, so we'll have to perform a hypothesis test to determine whether or not we have equal proportions. So we want to perform a test of the null hypothesis, the birthdays of all NHL players are evenly distributed among the 4 quarters of the year, against the alternative, that the birthdays of all NHL players are not evenly distributed among the 4 quarters of the year. They didn't give a significance level here, so we'll use our traditional alpha equals 0.05. Well, first we'll have to check our conditions, and if the conditions are met, we'll perform a chi-square test for goodness of fit. Well, random. The data come from a random sample of NHL players, so that condition is met. The 10% condition, because we're sampling without replacement, there must be at least 10 times the sample size, or 800 NHL players. In the season when the data were collected, there were 879 NHL players, so this condition is met. And finally, large counts. If birthdays are evenly distributed across the 4 quarters of the year, then the expected counts are all 80 times 1/4, because there were 4 quarters, or 20 total. These counts are all at least 5, so our large counts condition is met. Looks like we're okay performing a chi-square test for goodness of fit. Now, to perform the test, we'll have to calculate our test statistic. As we saw in the last example, we'll calculate observed minus expected squared over expected for each of the components, add up all of those results, and we get a chi-square value of 11.2. Now, as the excerpt shows here, chi-square of 11.2 corresponds to a p-value between 0.01 and 0.02. In the chi-square table, we have to look at 3 degrees of freedom because we had 4 different components we were looking at, and we see that 11.2 falls between these numbers, meaning the p-value is between 1 and 2%. Now, because the p-value, 0.011, which we get from technology, is less than alpha equals 0.05, we reject the null hypothesis. Therefore, we have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. For some additional practice performing a chi-square test for goodness of fit, try exercise 15.